Hi, I hope you're doing well today. Today we're going to talk about graphical vector addition using a protractor. And what you want to know today is that if you have graph paper, it may make it a little easier. Having lined paper is fine. Having plain paper, you're probably going to have some errors. So we only need really one direction of line. So this is this vertical line, or this is paper just turned, but what you need to make sure you do is have some sort of line on your paper to make this a little bit easier. So what we're going to do is talk about vectors. As you know, a vector is a graphical representation of a mathematical concept that has both magnitude and direction. It's a picture of math. And so examples of vectors would be something like 5 meters per second, or 7 meters, or 8 meters per second squared. So what we are going to do is add together a series of vectors that have both magnitude and a direction: 20 degrees, 30 degrees, 40 degrees. Now, before you could add together vectors, we need to make sure that we're adding together the same type of vectors. So this is a velocity vector, this is a displacement vector, this is an acceleration vector. We cannot add them together. They are different vectors. So when we're adding together vectors, we want to add together vectors of like type. So the vectors that we are going to practice adding together today are going to be things that I'm going to use that are called meters. Okay, we're just going to do displacement. Now, the other thing that we need to know before we actually do a real problem is that to add together vectors, we may need to scale it. So when you look at this protractor goes from 0 all the way over here to 180, and then it starts on 0 on the outside and goes over here to 180. We are going to be using what we're going to refer to later as a polar coordinate system. So in that system, 0 degrees is to the right, 180 degrees is to the left, 90 degrees is going to be up, and 270 degrees is going to be down. It is going counterclockwise from the positive x-axis, increasing in angle from 0 to 360. This is called the polar coordinate system. The other thing that you need to know about a protractor is that a protractor does or could have a measuring scale on it. This protractor here measures from 0 to 10 centimeters, or it measures in inches. We're not going to use the inches. We're going to use the centimeters. It's in here. If you don't have a protractor with a ruler on it, you're also going to need to get yourself a ruler, something to measure that length. Most protractors come with a ruler built in. We are going to try to scale everything to be within 10 centimeters. So that means if these were all the same units over here, they would be all less than 10 centimeters. But let's say I have different vectors. Let's say I have the vector 30 meters at an angle, and then I have another vector that's 50 meters at an angle, and I have another vector that's 60 meters at an angle. It's angle 1, angle 2, angle 3. Don't worry about the angles. They aren't going to change, but I can't draw a 30-meter line on my paper. 30-meter line is pretty long. So what do I need to do? I need to scale it. So scaling says that we take the 30 meters and we are going to multiply by a homemade conversion factor. So the conversion factor I am going to multiply by is that 1 centimeter is equal to 10 meters. Okay, I just made something up. I'm dividing this by 10. The units cancel, and now all of a sudden I have 3 centimeters. And then I'll have, for this one, can you guess it? 5 centimeters. And then for this one, I would have 6 centimeters. I just made a scale up. Whatever scale I pick, I have to use for all my numbers. So if I have the numbers 150 and 150 meters at an angle, and I add to that 5 meters at an angle, and then I add to that 120 meters at an angle, I can't scale this very well because these are so drastically different. I guess I could divide everything by 5, but I would have a 1 centimeter vector, and then I would have a 30 centimeter vector, and then I would have here a 20 centimeter vector. That would be pretty long if I divided everything by 5. We want to try to keep everything within 10. Everything I am going to give you this year is going to be scalable. So let's just imagine that this is instead of being 5 is let's make it an even 100. So in that case, instead of dividing by 10, because if I divide by 10, I would have 15, 10, and 12. That's still bigger than the 10, bigger than the 10 in the protractor. What I would need to do is divide this by another factor. I'm going to divide it by 20, and that would give me 7.5, 5, and 6. And those are very easy to draw. So an angle, this would be at angle 1, whatever it is. We don't change angle 1. Angle 1 doesn't change. The value of the angle doesn't change, just the scale of this number. This would be at angle 2, and this would be at angle 3. Okay, so using these numbers here, let's just actually use this set of numbers and put some angles with it. Let's do a vector addition problem. So the problem we're going to do is going to be, again, to take 150, and let's make that at 30 degrees plus 100 at, let's make that at 110 degrees plus 120 at 300, and just let's make it even 300 degrees. Let's add those together. So this scales, remember we're dividing these by, we're using the scale factor of 1 centimeter is equal to 20 meters. These were meters. And so I end up with 7.5 centimeters at 30 degrees. I get 5 centimeters at 110 degrees. I get 6 centimeters at 300 degrees. And to draw these, to add these together, there are a couple methods. We are going to do the graphical method first. I am going to have you do both the graphical and the algebraic method in here. We will do the graphical method today. We'll do the algebraic method tomorrow. We will practice these over the next week. And when we have a quiz, we will require that you do both methods, the graphical method and the algebraic method, in this chapter. Once we leave this chapter, we will then let you choose one of the methods. We don't need both of the methods, but you need to know which method you like. So now to add these together, to get what we call the resultant is the sum of vectors. To get the resultant, what we want to do is we want to take our protractor and we want to create an origin. That's what this little hole is on the protractor. This is our origin point. So I am going to set my origin right here on the paper. And now I am going to set my protractor on the paper and make sure my protractor is lined up with the horizontal bottom of the paper. Now, you could do this without lines. You could just look at the paper, look at the bottom of the paper, and make sure that it's lined up. But what we want to do, the advantage of having lines is I can look at these lines right here on the protractor and make sure they line up with the line on the paper. And that keeps my protractor, as I'm moving it around, so that 0 is always to the right. We want 0 always to the right. And so now I place this on here. I now see that my lines are lined up. And so the first step of adding this vector together is going to be to mark the 30 degrees mark. So remember, 0's to the right, 0, 10, 20, 30. It's right here. So I just put a little dot out there. 2 dots make a line. You could see I could make a line here. How long is that line? That line is going to be 7.5 centimeters. So I take my protractor, I place it on the origin. I place the second line so it's on line. 7.5 is all the way out here. So I draw my vector 7.5 centimeters long. That's vector 1. I then am going to take my protractor, the tip of the first vector. This is called the tail. This is the tip, the pointed part. The tip of the first vector becomes the origin for my second vector. Again, I have the lines on the paper to help me make sure that my protractor isn't tipped sideways. I only need I just need to make sure that 0 is to the right. So I check and I make sure that 0 is to the right, and now I'm going to mark 110 degrees. So on this protractor, we go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. So 110 is up here. I put a little mark. It's right in the middle of my numbers. That sometimes happens. I take my protractor and I tip it in that direction. The 0 mark lines up with the end of the first vector. I see the dot up here. I just make sure that everything is lined up. And now I draw to 5 centimeters. That doesn't draw all the way out to this point. This point's actually 5.5 out. It's okay. It's just giving us a reference direction. So I'm going to draw this line 5 centimeters. Okay, and that takes me right to there, right to there. I then am going to draw my last vector, which is 6 centimeters at 300 degrees. So I am going to line up my protractor, and I'm going to flip it over this time, because on the protractor, if you remember from what I said before, we have 0, 90, 180, 270, 300 would be down this way. So I'm going to turn over my protractor. Protractor only reads to 180, so this 90 is 270 down. Make sure it's lined up. So that's 270, 280, 290, 300. It's almost running right alongside the green line. It's actually 10 degrees further to the right than the green line here. And so what I'm going to do is make a mark. Again, 90, which is 270, 280, 290, 300. I made my mark. I now am going to place my protractor again, same way. This is the tip to tail method. Place the protractor with 0 right at the tip of the green vector. I line up my purple vector and line up with the purple dot. And I'm now going to draw my line, and it's going to be, in this case, 6 centimeters long. So it goes just past the dot. Okay, I'm off a little bit. I'm going to redraw that, just tipping this. I want to make sure that we're as close as possible. A little bit further to the right. You can see there's a tiny gap there. Okay, it's right there. And so now I've drawn my third vector. So this is the answer to the question, where is the sum of 7.5 centimeters plus 5 centimeters plus 6 centimeters with the angles that are mentioned here, 30, 110, and 300. The answer to that is they're right there. It's right there. So if you were trying to find the ordered pair from the origin, it's the ordered pair from the origin here of, here's my origin, remember that, 0, 0. So I'd say, oh yeah, the resultant is going to have us end right here. Now we want to know the actual distance to that point, because the sum of it really, what we would want is the magnitude and the direction. So what we're going to do is we are going to draw our resultant. The resultant will be drawn from the origin. This is very important. It's from the origin to the tip of the last vector. It's not the other way around. And so I line it up and I draw it. There it is. The red line represents. Take note, it is pointed in that direction. It's not from our end point back to where we started. It's from our start point to our end point. And so the length of that line ends up to be about 8.3 centimeters. And the direction of that ends up being, we place our protractor back at our origin, because what we're ultimately doing is measuring from our origin to our end point. The resultant is how we get from our start point to our end point in a direct path, single line. And so we put that there, and it reads out here 20. We have to look out at the edge, 20 and 160, and then the graduations 1, 2. It's about 2.5, so it's about 22.5. I'm going to say it's leaning towards 23, and so I'm going to say at 23 degrees. Now, I'm going to teach you tomorrow how to figure out this value algebraically. This answer here is going to have error in it. And we are going to allow in this class, whatever the actual algebraic answer is, there's going to be a very precise answer to this value. Whatever that happens to be, we are going to allow there to be a 5% error in magnitude and a plus or minus 3-degree difference in angle. And so if this value in reality was 8.25 at 22.5 degrees, this would fall within the error margin to get full credit. So there's an error margin that we have to live within, plus or minus 5%, plus or minus 3 degrees. We aren't done though. And I think that's a very important part of this. A lot of students finish right here. We need to scale this back out. If you remember, we had said that we divided this by 20. Well, to get our final answer, the actual final answer, we need to multiply this by 20 again, 20 meters per centimeter. That was our conversion factor up here. And so when we do that, we take 20 times 8.3. We end up with 166 at 23 degrees. So what's the answer to the question of what's 150 at 30, 100 plus 100 at 110 degrees, and 120 at 300 degrees? The answer is 166 at 23 degrees. You are going to want to practice these. There will be at least one of these on your next test. It'll be worth 2 questions. One question will be the magnitude, and the other question will be the direction. So it's a heavily weighted test question. It normally counts as 10% of your test. And then you also you may have a quiz on this before that point. So you're going to want to practice these. There's a number of these problems on my website. The answers are there. It is just a matter of practicing. It's the same process every time. Pick your origin, draw the magnitude and direction, then draw the next magnitude and direction, then draw the last magnitude and direction. Finally, figure out or measure the magnitude and direction from our start point to our end point. Make sure we scale it in and out appropriately and that we are not changing the angles. We're very cautious that we are using our protractor right and that we're not tipping it at any different angles, and you will get the right answer every time. Students get the right answer on this all the time. So my expectation is that everyone gets this right. You just need a little bit of practice. If you have any questions, please let me know.